please attempt the assessment quiz or the welcome back quiz by Friday so I can give you feedback for next week. And that's on Canvas. All right. And then you should have made or be trying to make a online homework account with WebAssign. I've only started homework for 2.1, but I haven't finished it. We haven't even gotten to notes for 2.1 yet. So I'm going to try to post that homework tonight, and we'll try to get to those notes today. But right now there's no homework to work on. There might be some homework tomorrow, but not today.
Professor? Oh, no, I mean Cassie.
Okay. If you're having trouble making your homework account, write an email to me and we can set up a time to meet and figure it out together.
Wait,
Right.
what kind of homework is it, by the way?
Last class, I started to just find domains and ranges of functions. I'm going to put those definitions on the board, the definition for domain, definition for range. But after doing those examples, I felt a little unsure of my answers, so I went and used 2 really good resources online. I'll put those on the board and I'm going to walk through those together. Or we'll do that together. Oh, and sorry, my sound.
Hello.
Okay, I can hear you now.
Okay, that's awesome. So by the way, what kind of homework is it gonna be? Is it gonna be like the homework on Alex or something? Or is it gonna be kind of different?
Let's see. It's the WebAssign homework is just like homework from the textbook, but once you put in an answer, if it's wrong,
it'll tell me.
It'll tell you it's wrong, and you can try again.
Okay, okay, so it's that kind of homework. Okay, awesome. That's a great way.
I like that because you get instant feedback. The only downside is it costs something. So.
Exactly. Yeah. It's just like Alex. They tell you what you got wrong, and then eventually, if you could take as much time as you want to understand it, it really works so well.
Yeah. And it's just in the syllabus, but just to remind you guys, if you miss a due date, just let me know and I'll give you more time because it's a good place to get our practice. Okay, we start with the definition of a domain. A domain is the set. Or let's say, we need a function first. Let f be a function. And we're still doing review. I think it is important to stop and understand these things. It's good to have a strong foundation when you're starting off with an important topic. So some other teachers might already be in chapter 2, but I think it's good for us to walk through a bit of chapter 1, just focusing on functions. So the domain is a set. It's going to be some subset of the real numbers in our class. It's a set of all possible inputs from the real numbers. And that real numbers part is kind of just specific to our class, so I'm going to leave it off from the definition. So the set of all of your inputs for your function is called the domain. The set of all of the outputs from your function is called the range.
Domain is X and range is f of X.
Yeah.
Okay, to make sure you know.
So you could call it y or you could call it f of x. They mean the same thing. They're equal to each other. For me, it looked weird at first, but after practicing for a while, it starts to make sense. One more definition. Oh, actually, just to note, the range is always a subset of what's called the codomain. And again, in our class, the codomain is going to be restricted to the real numbers. The graph of a function is also a set. I know usually we see it as a picture, but technically it's a set, and then we look at a picture of that set. Okay, it's the set of all ordered pairs x followed by f of x for all points.
So f of X is like, oh wait, no, never mind. I see it. Never mind.
Or you could call it like xy.
Yeah, XY. I was about to say that. Yeah, I was like, never mind. I already know that. I just saw the equation right there.
And the only requirement is just that x came from the domain of f. Okay, so this is kind of outside of something we would do in this class, but to write this mathematically, we would want to let f be a function. And then we're going to give the domain of f a name. We're going to say that k is, f is a function and the domain is called D with domain D. D is representing some kind of set. F takes values from that set over to the range. And we're going to call K the graph of F. Capital K. Usually for sets, we use capital numbers. And for functions, we often use lowercase lowercase letters. Okay, so K is the graph, which means K is a set of ordered pairs. So you start your set, all pairs x comma f of x are all xy. This bar means such that x is in the domain of D. I'm going to use a special symbol. Some of you may have seen it before. If you're going to continue taking math classes, you'll see it again. But this is your x, your inputs, and this symbol means exists in. Kind of looks like an E. There's a swoop with a line through, and it says exists in the domain D. Okay, so your graph K is technically a set of ordered pairs such that X is in the domain called D.
What, the line means such that, right? What do you mean by such that?
Such that, or like it's required that.
Oh, okay. So it means like require. Okay, got it.
Yeah, like this is the rule. This happens.
Okay.
Okay, so those are the definitions that I wanted to show you. Now there are 2 online sources that you can use to check your answers. I do feel it's really important that you attempt problems on your own on Scratchwork, but if you get stuck and you don't have anyone to talk to, you can go online. And the first place I would go is called Wolfram Alpha. This will give you a lot of answers, so you learn from practice and not just seeing the answer. So I would use scratch paper, and then check your work using Wolfram Alpha. I'll show you today. Also remember that when you're in class, you won't have this available to you. So you want to make sure you understand the material, not just the answer. Okay. Another place you could get some help from is called Desmos, and I like their graphing calculator. So what we're going to do is check over the examples we did last class using both programs just to show you how they look. And I did make one mistake, so we'll fix that mistake. And once we go through a recap of examples, we're going to move on to finishing the review, which is a recap of finding the slope of a line. All right, so let's put up those examples and then I'll show you how they look first in Wolfram, then on Desmos. Okay, we're going to start with Wolfram Alpha. So just Googled it. This picks the first link. And in here you can type your math. We're putting in the function f, which sends x to x. And then it says it's a line. And then if you scroll down right here, it tells you the domain, all real numbers, which we had before. It tells you the range, all real numbers. If you go to Desmos, you can see a graph of the function. And from the graph, you read from left to right for x values. So you can go all the way to negative infinity on this graph and all the way to positive infinity. For the range, you look at y values, and this graph has y values towards from negative infinity up to positive infinity. Okay, so we did this before. It was all real numbers. And this one too. Then we had a function f, and it's equal to 2 over x minus 5. So I wanted to check my domain and range using those programs. Let's start here. Same name for a function, but this time the outputs are 2 divided by the quantity x minus 5. Okay, so this time I did get some little graphs that I could look at instead of using Desmos. And you can also scroll down to see the domain and range. So from the graph, your x values are the values going left to right. You can come from negative infinity over to 5, but there's no actual piece of the graph right where you have x equal to 5. So leave that out of the domain. And then you can start again after 5 and have values over to positive infinity. That's your domain. Everything except for 5. The range is from like up and down for your y values. So you're going down from negative infinity up to 0, but there's no value for your graph right here at y equals 0. And then you have y values really, really close to 0, positive y values, and then they keep getting larger and larger and larger. And this side you have negative y values getting close, close, close to 0, but not equal to 0. So you need to leave 0 out of the range. There's no number that you can put into that function to have an output of 0. You can't take 2 and divide by some number and somehow get 0.
Oh wait, the equation is 2 over x minus 5, right?
Yeah.
Okay, so so I understand why it's like 5 cannot count because the 0 cannot, because the bottom cannot be 0. Okay.
Yeah.
And
then you think, how can I put some number in for x and have this value here be 0? You can't. I would maybe play around with that on scratch paper, like put in different x values and see that you can't get 0. Okay, or you can look at a graph. So we're going to put in.
Also, that R, that means all real numbers, right?
Yeah.
Okay, yeah.
So here we are, 2 over x minus 5, looking at the graph. Your domain goes from left to right, negative infinity, and then there's this whole vertical asymptote at x equals 5, no value there. And it starts again after 5. Then you go up and down for range, down from negative infinity, up very close to 0, but not equaling 0. And again, positive values that are close to 0, but not equal to 0, and they continue up to infinity. This is a mistake I made last class that we can fix now that we've checked it. And then then we had, I think, two more. Next one was a new name. This function is called j. J of x is the square root of x plus 3.
Wait, does JX equal the same thing as FX?
Kind of. It's just a different name. So I called this one f and I called this one j.
But still the exact same thing. They both equal Y, right?
Yeah, it's an output. Yeah, you could call j of x y.
Okay, yeah.
And then we did this last class, but I want to show you how to do it using the Wolfram Alpha website. Our outputs are j of x values that look like square root, which to type that is sqrt, square root of x plus 3. And then this also gives a graph. And then further down, you have your domain and range. So the domain was all x values that are real numbers, such that, that's what those dots mean, is either a bar or a line, but such that x is greater than or equal to 3. So looking at this graph, you go left to right for your domain, and you can go all the way to -3 and include -3, and then to the right towards positive infinity. For the range, it's all values of the function that are real numbers. So that j is your outputs of that from that function j, and then exists in, and it says real numbers, such that j is greater than or equal to 0. So your outputs for this function have to be greater than or equal to 0. Which you can see in the graph. If you go here, it goes far down on the y-axis as 0, and the graph goes up and up and up and up and up and up. It keeps going up to positive infinity. And you can see the same graph in Desmos if you want to. Again, you'd have to put in.
So when we try to like do these kinds of questions, the first thing we should do is like graph it, right?
I think a graph would help. It would
Yeah.
definitely help if you can. Okay, and let's put that answer down. All right, we did one more example, then I like to go on to a new topic. So hopefully it makes sense how to use Wolfram Alpha for checking your answers, but
Wait, are we still on J? JX?
no, we finished that one. We're on to a
Oh,
new
okay.
function. Yeah, from j of x, we just want domain and range.
Okay.
F of x
Oh, we're doing something else. Okay.
is
Yeah.
now like this. last one. So you want to do this caret and then 2, so it's x squared. Okay, you get a graph of a parabola. And you get your domain and range. Domain is all real numbers. You can go all the way to the left and all the way to the right. The range is values starting at 0 and then up to positive infinity. So all values of a function f that are real numbers such that f of x or your y, your output, is greater than or equal to 0. And you can find the same graph on Desmos.
Wait, what does the E mean again? It means in, right?
In, yeah, exists in.
In, okay. Yeah, just gotta make sure.
Or it says like your value is an element of. So it looks kind of like element or something.
Yeah.
Now something new and kind of wrapping up the review. So it's the definition for average rate of change. And then we'll practice that and then we get to start chapter 2. So back to just taking notes. Those were just examples we had already done. I just wanted to show you how you could check your answer online. So the average rate of change between 2 points, x1 and f of x1. The other point is x2 and f of x2. So x subscript 1, x sub 1, and then followed by f of x sub 1. F of x1, and then you have parentheses around that to show that it's a pair. This one first, and then your output next. The other point is x2 followed by f of x2. It's the slope of the line between those 2 points. So if you remember how to find the slope of a line, you take your difference in y values and divide by the difference in x values. This average rate of change is also called the slope of the secant line. slope secant line and is denoted pretty sure it's read as m secant. So m sub secant. M for slope. The subscript secant for slope of the secant line. So m subscript secant is the slope of the secant line through these 2 points. And you find slope by taking difference in y values, f of x1 subtract f of x2.
Wait, that m with sec, that means the slope of the second line, right?
Yeah.
Okay, and it's basically the equation for the average rate of change between 2 slope points, right?
Yes.
Or okay. Okay. Yeah.
I'll mean the same, and you got it. Okay, and if you remember finding the slope of a line, you need your subscripts to match. So if there's an f of x1 here, x1 starts, then subtract x2.
I think this is similar to a one equation where you find like a distance of the slope or something, or like try to find a slope or something. You know, like y2 minus y1 over x2 minus x1.
Yeah, exactly. It's just a little bit different notation, but you've got
Yeah.
the right idea.
Wait, is that the equation for finding a slope, right?
Yes.
Okay, just gotta make sure. Yeah.
This is a special slope for a special line, but it's overall just getting the slope. So it could also look like this. And again, your subscripts just need to match. So if it starts with f of x2 in the denominator, start with x2. And then subtract x sub 1. Okay, then we practice. So here's an example. Before we do an example, I'm going to draw just a basic picture, and then we'll get into one.
Wait, those two equations, even though you convert them, they still mean the same thing, right?
Yeah.
Okay, okay.
This one, you'll get the same answers if you did this one.
Okay.
Thanks for asking questions, by the way. It helps everybody in the class, including me. So we're going to have a basic curve. Find some coordinate. Just draw something like this. And then there's 2 points on that function. We'll go right here. So we'll call this one of your x values, and we'll call it x sub 1. And this point is x1 followed by f of x1. And that number f of x1 is sitting right here on the y-axis. It's a y value. It doesn't look good. Let's stay here. Okay, I'm going to put my other point down here. So right here, there's another point on your graph. I want to call that, or I choose to call that input x sub 2. And that point is x sub 2 followed by f of x sub 2. So close the parentheses around x sub 2, and then close the parentheses around this pair, x2, f of x2. This number f of x2 is a y value over here. Some number f of x2. Okay, and then if you draw a line through those 2 points, that's the secant line. The secant line crosses a curve more than once. Let's draw that. Use red. I'm going to do my best to draw a straight line. Okay, the red line is a secant line. It's a line that crosses a function more than once. And the slope of that line is the average rate of change between those 2 points. And it's that m subscript secant. Okay.
Oh, so like that m secant formula is gonna solve for that red line, right? That this is between like that, right?
It's going to be a piece of the line. It's going to be the slope. So only the slope from the line, not the whole line.
Okay.
Yeah. I think an example is going to help what you're going to do right now. Okay, f of x is x cubed minus x. Find the average rate of change of f from x1 being 0 to x2 being 2.
Nope.
Okay. So find the average rate of change from one input to another means find the slope of that line through the 2 points on that function. So we want m sub secant. Slope of the secant line, which would be, oh, we need more scratch work. Okay, we'll put it in the formula, but we need to go on the side and get values. Let's try f of, I did x sub 1 minus f of x sub 2 over x1, x sub 1 minus x sub 2. I'm gonna figure out what that number would be. Okay, f of x1 would be f of 0. And you're putting it through that function. F of 0 equals 0 cubed minus 0. 0 minus 0 is 0. So I'll be able to put that number in right there and then subtract whatever that number is, which we'll figure out. F of 2 is f of 2. So just substitute this with that. And you have a 2 cubed minus 2. Which would be 8 minus 2, which is 6. So now I can go over here and keep finding this slope. Write this one more time so it's nice and neat.
Wait, just for like memory purpose, can you rewrite that question again? Like, because like I think some people might forget what equation we're talking about, you know?
Yeah, we'll put it here.
Yeah. Perfect.
So we've got this formula. Just copying it down again. You know that number? It's 0. Number 6. And x1 was equal to 0. And this x2 number, I can see it right here, x2 was 2. Negative 6 over negative 2. And there's a negative, but the negative is positive 3.
3. That's just a positive, yeah.
So the slope of the secant line is 3. And then we're going to continue. Let me see. We could continue to find the equation of the line. If you remember, you can use something like y equals mx plus b, and use this for your m, your slope. But that's something we'll get to, which I think we'll start chapter 2 now. So again, don't let domain and range scare you away from the class. There's resources to help you with those parts. I can help you with those parts, but it's not the main focus this semester. This is the focus, tangent lines / derivatives. So we're starting chapter 2.
Wait, sorry. Was this still also a review? And now we're getting into like the actual. Okay.
Yeah, we just
Perfect.
ended review.
Okay, perfect.
Awesome. So review doesn't mean that you should already know these things. Review means these are important parts of our foundation for studying calculus. So I want you to know or have somewhere in your notes what it means, but let's get into something kind of different, chapter 2. I'm gonna at least introduce this topic, but we'll come back next time because we're almost out of time. It's about tangent lines and velocities.
Mm.
Let's do one definition and then we'll call it good. So a tangent line to a curve is a line at a point that models the behavior of the curve right at that point. Line. Tangent line. It is a line, but you don't need to put that. A tangent line to a curve or function. Okay, it's a line at a point. Quick picture, and that's it for today. So let's say you have a curve. Yeah, it's a circle. And then somewhere right, like say right here, I've got a point and then a tangent line that describes the behavior of the curve right there. So it's a line that just touches, it's a straight line that just touches the curve right at that point. A secant line goes through the curve more than once. So if you go through this point and this point, it's called a secant line.
Mental stuff.
And a secant line is a line that intersects the curve more than once.
Intact.
We'll come back and draw more pictures and do more examples, but that's it for today.